Video, we're going to apply the arc length formula to a problem involving estimating distances to far away objects. So this says the measure of an angle that an object subtends out at our eyes when viewed from a distance is called the object's apparent size. So really what this is getting at is that if you're looking at distant objects like the Earth, not the Earth, the sun or the moon or distant stars, obviously they all have different sizes, apparent sizes from where we're viewing, but that's only because they're at various distances from our eyes. So the size that something appears to us is not just a function of how big it is, but also how far away it is. So its apparent size is the angle that basically the top and the bottom of the object in our visual field makes with our eyes. So this angle here is the apparent size, and the idea is when objects are really far away, the diameter of the object, so for instance the exact diameter of this let's just say it's a planet, might be that, but really it's very, very, very close to what I'm dashing in there, which is the arc length of the section of a circle where we think of our eye as being at the center of a circle. So ultimately, we're just going to use arc length to estimate the diameter of a circle by basically assuming that the arc length and the diameter of the circle are identical. So, and of course, the farther away the object is, the better that estimation is. So let's look at this example. It says Jupiter has an apparent size of 0.01 degrees when viewed from Earth, and that's 8 times 10 to the 8th kilometers from Jupiter. We want to find the approximate diameter of Jupiter. Okay, so let me just draw this picture here. So what we're saying here is we've got our planet Jupiter. Let's kind of move it into roughly a good location. This will be fine, I think. Okay, so we're estimating the diameter of Jupiter. We know that this angle here, the apparent size, is 0.01 degrees. And we also know the distance from Jupiter is 8 times 10 to the 8th kilometers. And what we're trying to approximate here is the diameter, which we're going to, for our purposes, we're going to assume is that arc length there. So just a quick review of arc length if you haven't. I'm hoping that you're coming to this video knowing what arc length is, but just as a quick review of the formula we're about to use, right? In a circle, that's the central angle, that's the radius. S there is the arc length. You think of that as a fraction of the circumference. So we would say that this arc length here is theta 3/60ths of the circumference of that circle, which is 2 pi r. So that's the formula we use. So we're going to say that the diameter, so I'm going to just indicate that that's the arc length, which is about equal to the diameter. So the diameter is about equal to the arc length, which we know is theta 3/60ths, so 0.01 3/60ths times 2 pi, and our r is 8 times 10 to the 8th. Okay, so punching this into our calculator, we'll see what we get here. Okay, so we punch in 0.01 divided by 360, enter, times 2 pi times 8 times 10 to the 8th, so, and that gives us about 139,000, we'll round to the nearest kilometer, 139,626 kilometers. That's our estimate for the diameter of the moon. Let's try another one that's a little different but related. Let's say we know the diameter of the moon is 3,500 kilometers. Its apparent size is 0.008 radians. Okay, radian is just another measure of another way of measuring angle, as far as we're concerned here, as opposed to degrees. How far is it from the Earth? So again, in this case, we'll say that's the moon. So the apparent size is the angle our eye sees, or our eye is recording, really. Okay, so this time it's in radians. I'll point out in a second what that means. Now, we're given the diameter of the moon, but basically we're just going to assume that the diameter is interchangeable with the arc length that would be right, that we would see if we were assuming that these two purple lines here were the radii of a circle. Now, the moon is closer than distant stars like Jupiter, so the error here might be a little bit more than when you're doing this with objects that are farther away. But again, as an estimate, it's probably fine. So we know that the diameter is 3,500 kilometers. Let's just say that the diameter is about equal to the arc length, which we're going to say is 3,500 kilometers. Okay, and it says the question is, how far is it from the Earth? How far is the moon from the Earth? So again, we're assuming that's his Earth. So we're looking for this. I'm going to call this r because we're thinking of this as the radius of a circle. Now, in this case, just one thing to point out is that when our angle was in degrees, we saw that this formula gave the arc length when you're in degrees, but we're in radians, so you can either convert to degrees, but it's probably easier to note that 360 degrees is equal to 2 pi radians. So with that in mind, we're going to use this formula, this version of the formula, which is theta over 2 pi times 2 pi. So we get a much cleaner formula when we're in radians. So S equals theta times r, where we're thinking of S here as basically our estimate of the diameter. Okay, so we know everything except the radius in this case. So our S is 3,500 kilometers. We don't really need the units. And our apparent size is 0.0087 radians. We're trying to find the radius, so that must mean that r is 3,500 divided by 0.0087, which is about we'll say 402,298. Okay, that's the estimated distance from the Earth to the moon, given this is the apparent size.